All right. Hello, welcome to this presentation about the paper titled Quantifying the Confidence of Anomaly Detectors in Their Example-Wise Predictions. I am Lorenzo from DTAI Lab of KU Leuven in Belgium, and I have done this work together with Vincent and Professor Jesse Davis from KU Leuven as well. I want to motivate this work by applying an unsupervised anomaly detection algorithm to the shown two-dimensional synthetic dataset. While the labels are unknown to the detector, the circles are normal examples and the triangles are anomalies. Our goal here is to make a prediction for the test example denoted by the cross mark in the picture. So what would it be your prediction in this case? Would you predict normal or anomaly for the test example? Well, in this scenario, the predicted class is normal, and as you can easily imagine, the output strictly depends on the training set. So an important question that we want to raise is, does the prediction change when a different training set is drawn from the same distribution? In other words, how confident is the model in predicting the normal class for this test example? By drawing three different training sets from the same distribution, it may happen, as in this case, that the prediction changes. Here, in fact, the model predicts twice the normal class and once the anomaly class for the same test example when trained on different training sets. Then, how much can you trust the model? As I said, 2 times the predicted class is normal, but then would you be more confident in predicting normal in the first or in the second case? Maybe in the first one, because according to our intuition, the test example might be more normal since it is closer to the normal data rather than to the anomalies. So what we actually propose in this paper is a measure of confidence in predicting the same class when different datasets are observed. In fact, if you have a look at this animated GIF, you will see that by drawing for 20 times different datasets, half of the times the unsupervised anomaly detector predicts the normal class, and half of the times the anomaly one. The prediction of that example seems to be extremely related to the observed training set, and the goal of our paper is to measure this quantity that we call confidence. Additionally, the confidence measure allows cross-comparison among models. In general, it's quite tough to select a prediction when different models disagree on the final class. In this case, for example, if you train two different anomaly detectors on the same dataset and you assume that these two models are equally accurate on average, then a potential choice might be to pick up the most confident method in its prediction, as we should probably trust it more. In fact, many times it might be better to avoid prediction with high uncertainty and rather prefer more confident models. So how would you estimate the confidence of a model in its example-wise prediction? In this paper, we made 4 contributions. First, we defined the novel topic of confidence as the probability that a prediction would change if a different training set was observed. This is valid for any anomaly detector. And second, we introduced Exceed, a model which is able to estimate accurately the confidence of any anomaly detector in 2 steps. Firstly, it transforms the anomaly score into the outlier probabilities with a Bayesian approach. And secondly, it derives the confidence values by observing that different training sets lead to different thresholds and in turn to different predictions. Our third contribution is an extensive analysis of the convergence of Exceed's estimates. And finally, we evaluated our model on a large number of benchmark datasets. But let's start by giving the intuition again behind the confidence measure. The first idea to capture the uncertainty in class prediction by using an existent method might be through a density estimator, which is able to produce the outlier probability, which is the probability that one example belongs to the anomaly class. But if you have a look at this animated GIF, you will see that although the predicted class changes many times, the outlier probability keeps being high. It seems that even though the anomaly detector predicts many times the normal class, the test example has very high probability to belong to the anomaly class. As a result, density estimators do not capture uncertainty in class prediction, but something different. We then introduce a novel measure of consistency that we call confidence. In addition, we introduce the method called exceed for estimating the confidence that is able to capture this uncertainty in class prediction. For instance, using the same setting as before, the confidence value of predicting the normal class is always around 60%, meaning that if we drew several and potentially infinite datasets from the true distribution, then 60% of the times the model would predict the normal class for that test example. In contrast, when the outlier probability is equal to 80%, then it means that 80% of the scores equal to the one of the test example belong to the anomaly class, no matter of the prediction itself. So the outlier probability and the confidence are two different topics. The outlier probability measures the probability that one example belongs to the anomaly class, and it is totally disconnected to the actual prediction. In contrast, the confidence measures the consistency in predicting the same class as the model is currently predicting, and as a result, it depends on the actual prediction. But now let's go into details, starting from summarizing a bit the standard process of an unsupervised anomaly detector in 3 steps. Assuming that no labels are available, the anomaly detector first maps each unlabeled example into an anomaly score, which represents its degree of anomalousness, where the higher is the score, the more anomalous is the example. The second step consists of sorting the anomaly scores in order to put the anomalies at the top of the ranking. By doing this, and by assuming that the expected proportion of anomalies is given, the model sets a threshold such that above it, in the ranking, there is exactly the same proportion of examples as gamma indicates. Since the higher the position in the anomaly ranking, the more anomalous is the example, in the third step, the model predicts anomaly for all the examples with greater score than the threshold and normal for all the scores below it. So observe that considering a different training set would lead to different threshold and consequently to a different prediction. This will be the main key under our method. Let's now pass to the methodology and to our model exceed that aims to estimate the pointwise confidence of any anomaly detector in 2 steps. In the first step, the main goal is to pass from the anomaly scores to the outlier probabilities. Let's start by fixing a score S, which is the anomaly score of a fixed test example. As the higher is the score, the more anomalous is the example. What we want to do is to measure the quantity of scores that are less than S. In fact, it's easy to realize that the larger the number of examples with lower score, the greater is the red area quantifying the anomalousness of S, and as a result, the more anomalous the score S is. So the first step consists of estimating the red area inside the plot, which is the probability that drawing another example and computing its anomaly score, this new score will be less than our fixed value S. And in practice, as we do not know the actual distribution of scores, we assume that the red area is a random variable with non-informative prior uniform distribution, and by considering the anomaly scores inside the dataset, we model the posterior distribution and take the mean as the most likely value. The Bayesian approach allows getting smooth values of the red area, as it is the same as considering the empirical distribution of anomaly scores with a correction factor. In the second step, we have smooth probability values PS representing the red area, which again might be thought as the probability that drawing a new anomaly score from its true distribution, this will be less than the fixed score S. In this step, we should quantify the confidence assuming that different training sets are observed. But instead of literally drawing many training sets, we just need to consider the score that the anomaly detector would assign to each drawn example. And the main key insight here is that we do not need the actual value of the anomaly scores, but only whether these are greater than S or not. In fact, it doesn't matter the distance between the threshold and the score S, but only the side of the threshold with respect to the score. What we should do to pass from the outlier probability to the confidence value is to calculate the number of examples that would end up inside the red area if we drew a different dataset with the same size as the previous one and assuming to know the previously estimated outlier probability PS. In fact, in order to set the predictive threshold such that the fixed score S is predicted to be anomalous, we just need that enough examples fall inside the red area. And formally, this is nothing more than a binomial distribution. Inside the paper, we also perform a theoretical analysis of how increasing the size of the training set affects our confidence estimation. To do that, we consider two different cases according to the expected proportion of anomalies inside the dataset. If a few anomalies are expected to be present, then the confidence will converge to 1, and the limit predicted class will only depend on the value gamma. In fact, if the proportion of examples in the training set with anomaly scores greater than S is high enough compared to gamma, then the example will always be predicted as normal. On the other hand, assuming that the training set will never contain anomalies and taking the maximum score as threshold, then the confidence either converges to 1 in case of an example with greatest score is observed, or otherwise it converges to e powers to -1. This particular and not so high value in the second case is due to the fact that while the training set is growing in size, it gets more likely to draw a normal example with anomaly score greater than the fixed test score S. And if eventually it happens, then as you can see from the test 2 in the plot, the predicted class will change to normal and the confidence will converge to 1, as in the first case. For this reason, it's not very likely that the test example will end up remaining anomalous to the limit. Our last contribution regards the experimental setup. To empirically prove the effectiveness of EXCEED, a large experimental comparison has been performed. We consider the error between the confidence estimates and the empirical frequencies of the class prediction, and we compared our method with 3 baselines. The first baseline consists of assuming that the model has always confidence equal to 1 in its prediction. And the second one consists of using the existing density estimation methods instead of our step 1. And finally, the third group contains the calibration methods where we actually have to assume that the training set is labeled. By involving 3 anomaly detectors and 21 benchmark datasets, we prove that our method EXCEED is able to recover the empirical frequencies of the class prediction better than the other baselines. A final example illustrates that EXCEED is able to estimate the uncertainty in class prediction differently for slight different examples. Consider the case where an example starts moving away from a normal cluster of data towards anomalies. In this case, we expect that the confidence start high and get lower while the example is getting less normal. Then after a while, the model is supposed to change its prediction from normal to anomaly, and the confidence should get higher again, meaning that the point is getting more anomalous step by step. The strength of EXCEED is that it is able to produce smooth confidence scores which capture the variation of uncertainty behind the model, even if the example's position slightly changes. To summarize the paper in a nutshell, the confidence is a novel measure that captured the probability that the predicted class would change if a different training set was observed. Through our method EXCEED, it is possible to estimate the confidence of the example-wise prediction of any anomaly detector. And by both a theoretical convergence analysis and a large experimental setup, we prove that EXCEED accurately recovers the confidence scores and behaves as our intuition would expect to. For any further information, you can have a look at the paper and find the code on my GitHub page. And you can also contact us via email. And thank you for your attention.